All right, everyone, let's get started with today's lesson, lesson 11, the uncertainty principle. So if you'll get out your study guides, let's take a look at this uncertainty principle. All right, so let's go back a little bit with Niels Bohr. Niels Bohr is going to be the very first individual to really develop a model of the atom based on quantum theory. And prior to really that model, scientists were basing their models off of classical physics ideas, and just weren't working so well. And Niels Bohr is going to take a stab at it with his new model. And basically, if you recall, uh, it's basically going to take the electron and put the electron in certain quantized energy levels, meaning that the electron can only be at specific distances from the nucleus. And the electron is only allowed to be at these specific quantized levels of energy and nothing in between. In other words, there seems to be a limit to the quantity of energy that an electron can have within the atom. And therefore, the electron can never crash into the nucleus because it could not lose enough energy to do so. Its lowest energy state in the atom is what is known as the first principal energy level, which we've talked about in previous lessons. So Niels Bohr is taking a shot at this, and he's making some headway with the fact of taking the electron and finally saying that it looks like the electron exhibits some type of quantum behavior, and atoms in general represent some kind of quantum behavior. Now, all of his work worked very well for the hydrogen atom, but when it started applying to other atoms, it wasn't working as well as he would have liked. And so, yeah, getting there, but not exactly on the right, it's just not right, okay? In other words, the Bohr model is good, but it's not great, it's not right, in fact, okay? And so it comes down to the fact that there's still some issues with the electron. What is going on with the electron? It appears that it has some kind of quantum behavior, but what is that? What do we mean by that? What's going on? All right. And Niels Bohr couldn't really solve that, and neither could others at the time. But shortly after, let's jump into this. Shortly after, a French mathematician physicist named Louis de Broglie solved the issue. He solved the case, all right, more or less. What de Broglie began to understand was that the electron was very similar to light, and that is that the electron not only had a particle behavior to itself, but also had a wave nature. In other words, the electron is both a wave and it is a particle, just like light, okay? Which gives it its quantum behavior. This was confirmed by experiments in 1927. So essentially, let's look at the electron in this way. Very similar, you got to think about light, all right? And that is the electron can exist in both states simultaneously. So it can be a particle and a wave at the same time, just like light, okay? It is not until the act of observation that forces the electron to be either in one state or the other. In other words, which state of the electron is observed is dependent upon the experiment that's being done. This is very similar to light, right? In the atom, when electrons behave as both waves and particles at the same time, the wave nature then of the electron explains the existence of stationary states in the Bohr model, so these energy levels. So Bohr was completely focused that the electron was particle only. And therefore, all of his calculations were based on the particle nature of the electron. But de Broglie is demonstrated that the electron behaves as both a particle and a wave. It's both simultaneously. And therefore, this would explain the electron shells, or those energy levels, those quantized energy levels that the electron basically has, or in other words, the atom has, and the electron is found in those locations, okay? Now, this then also describes how the electron does not crash into the nucleus. So, wow, this gives us some much better direction than we had before. Now, it's very interesting because it turns out that all particles, all matter, you, me, elephants, planets, everything has both a particle and a wave nature. All right, and this was really confirmed in 1927. So wait a minute, you're saying that you are a wave and a particle? Yeah, that's what we're saying. The problem is, though, that you're really big, okay? No offense. The bigger the object, the less likely it's to have its wave nature exhibiting or showing very often. In other words, it's really hard to tell that a big planet or a big object has a wave characteristics at all. The wavelengths, it's not, when you look at it this way, the larger the object, the larger the wavelength. And so the less likely it seems that it has any wave characteristic, even though it does. But when you look at atoms and you look at electrons or photons of light, because those particles are so tiny, they exhibit much, much, much smaller wavelengths. And therefore, they begin to look more like waves and less like particles. So all this time, we've kind of started our understanding of electrons clear back with J.J. Thomson's experiment, cathode ray tube experiment, that electrons exhibit only particle behavior. And therefore, we assumed that the electron was only a particle. And therefore, all of our calculations, mathematics, and models were built on the very fact that the electron is a particle and not a wave. But now, we can't do that any longer. We must consider the fact that an electron exhibits both wave and particle characteristics at the same time, and that it occurs in atoms, okay? And this is going to change our direction now with electrons in atomic structure. Now, by doing this, this introduces a very important principle called the uncertainty principle, or Heisenberg's uncertainty principle. Now, let's give you a little bit of an idea of what this principle means. Whereby not any stretch of the length where we're going to get into great details into the uncertainty principle. We're just going to state some facts that we need to know and understand for our class, and specifically for what we need to know about the structure of the atom, okay? So it's important to understand that we cannot simultaneously observe both the wave nature and the particle nature of the electron, okay? We can't observe them both at the same time, in other words, is what we're saying. Even though they both exist, the particle nature and the wave nature of the electron, just like light, exist at the same time. but we can't observe that. We cannot see that. We can only see it being a particle, or we can only observe it being a wave, but not both. That brings in this idea of uncertainty, okay? So observation, then, will force the electron to be seen as a wave or as a particle, but not both at the same time. Consequently, our inability to observe the electron simultaneously as both a wave and as a particle means that we cannot simultaneously measure its position and its velocity, okay? Because it has both natures existing at the same time, but we can't observe both natures, we cannot know the position of the electron, nor can we know the velocity, which means really the energy of the electron at the same time. We just can't know that. So this brings in what is known as uncertainty, okay? This uncertainty of the position and the energy or the velocity of the electron is known as the Heisenberg uncertainty principle and has vast consequences. Heisenberg's proposed the uncertainty principle in 1927. And the Heisenberg uncertainty principle basically states that the more accurately we know the position of an electron, the less accurately we know its velocity or energy, and vice versa, okay? If we know how much energy an electron has, then we really don't know its position very well. We don't know where it's found, okay? So take the consequences. Sorry about that, the lights went off. Take the consequences of this, okay? Either I know where the electron is located at in the atom and not how much energy it has, or I know how much energy the electron has, but I don't know its exact location or position, okay? That's what we're really talking about this. So because of the uncertainty principle, electron is observed as either a particle or a wave, but neither at the same time. So what do? Do we observe the electron in the atom as a particle, or do we observe it as a wave? What works best? Well, as you're going to see briefly, okay, into the next lesson, we are going to observe the wave nature of the electron and not the particle nature as much, okay? What does this do then? Well, it allows us to now determine the precise or the accurate, maybe that's the better word, the accurate amount of energy that the electron has, but it does not allow us to accurately determine the position or the location of the electron in the atom. We have no certainty of its position in the atom, is what we're saying, okay? So this principle is important. These thoughts are important. So you gotta start thinking about it in terms of the electron behaving as a wave and as a particle at the same time, but we can only observe one or the other. We cannot observe them both simultaneously. So this brings in uncertainty into the position or the energy of the electron, okay? Now, what I want to do to finish this up is just to show you a short video about the uncertainty principle, okay? Let me get that on here for you. All right, here we go.
The Heisenberg uncertainty principle is one of a handful of ideas from quantum physics to expand into general pop culture. It says that you can never simultaneously know the exact position and the exact speed of an object, and shows up as a metaphor in everything from literary criticism to sports commentary. Uncertainty is often explained as a result of measurement, that the act of measuring an object's position changes its speed, or vice versa. The real origin is much deeper and more amazing. The uncertainty principle exists because everything in the universe behaves like both a particle and a wave at the same time. In quantum mechanics, the exact position and exact speed of an object have no meaning. To understand this, we need to think about what it means to behave like a particle or a wave. Particles, by definition, exist in a single place at any instant in time. We can represent this by a graph showing the probability of finding the object at a particular place, which looks like a spike, 100% at one specific position, and 0 everywhere else. Waves, on the other hand, are disturbances spread out in space, like ripples covering the surface of a pond. We can clearly identify features of the wave pattern as a whole, most importantly, its wavelength, which is the distance between two neighboring peaks, or two neighboring valleys. But we can't assign it a single position. It has a good probability of being in lots of different places. Wavelength is essential for quantum physics because an object's wavelength is related to its momentum, mass times velocity. A fast-moving object has lots of momentum, which corresponds to a very short wavelength. A heavy object has lots of momentum even if it's not moving very fast, which again means a very short wavelength. This is why we don't notice the wave nature of everyday objects. If you toss a baseball up in the air, its wavelength is a billionth of a trillionth of a trillionth of a meter, far too tiny to ever detect. Small things, like atoms or electrons, though, can have wavelengths big enough to measure in physics experiments. So if we have a pure wave, we can measure its wavelength and thus its momentum, but it has no position. We can know a particle's position very well, but it doesn't have a wavelength, so we don't know its momentum. To get a particle with both position and momentum, we need to mix the two pictures to make a graph that has waves, but only in a small area. How can we do this? By combining waves with different wavelengths, which means giving our quantum object some possibility of having different momenta. When we add two waves, we find that there are places where the peaks line up, making a bigger wave, and other places where the peaks of one fill in the valleys of the other. The result has regions where we see waves separated by regions of nothing at all. If we add a third wave, the regions where the waves cancel out get bigger, a fourth and they get bigger still, with the wavy regions becoming narrower. If we keep adding waves, we can make a wave packet with a clear wavelength in one small region. That's a quantum object with both wave and particle nature. But to accomplish this, we had to lose certainty about both position and momentum. The position isn't restricted to a single point. There's a good probability of finding it within some range of the center of the wave packet. And we made the wave packet by adding lots of waves, which means there's some probability of finding it with a momentum corresponding to any one of those. Both position and momentum are now uncertain, and the uncertainties are connected. If you want to reduce the position uncertainty by making a smaller wave packet, you need to add more waves, which means a bigger momentum uncertainty. If you want to know the momentum better, you need a bigger wave packet, which means a bigger position uncertainty. That's the Heisenberg uncertainty principle, first stated by German physicist Werner Heisenberg back in 1927. This uncertainty isn't a matter of measuring well or badly, but an inevitable result of combining particle and wave nature. The uncertainty principle isn't just a practical limit on measurement. It's a limit on what properties an object can have, built into the fundamental structure of the universe itself.
All right, so I hope this kind of gives you a basic understanding of the uncertainty principle. So in summary here, the electron, just like light, has a particle and wave nature state that exists at the same time. However, our observations, when we observe the electron, we can only see it either as a particle or a wave. And it just depends on the experiment that we run, determines which state that we see it, particle or wave, okay? Now, because of this, we can never see a wave of an electron and a particle of an electron at the same time. Therefore, that builds in uncertainty into the position that the electron is found and the momentum, okay? As a wave, the wave position can be in all sorts of places because it radiates out, all right? So therefore, an electron, looking at it in this wave-like idea, you can't know its position at all, but you can know the amount of energy that the electron has if you're looking at it as a wave. If you look at it as a particle, you may know the position of that particle at any given time, but you don't know its energy or how much energy it really has. And that's where Bohr was having problems at, and why the Bohr model works to a certain degree, but not much, because he did not account for the uncertainty principle and the fact that the electron behaves as both a wave and a particle. Okay, so there you go, the uncertainty principle. Hopefully this makes sense. So good luck, study hard, and we'll see you later.